Hello, everybody. My name is Amanda Katona, and I'm the SC19 Communications Chair. Welcome to the SC19 Press Conference. My team is available here to assist you with any questions while you are here, so please don't be afraid to ask if we can answer any questions for you. Most of us are kind of in the back right now. We have a professional photographer here this week who will be covering all the shows and the photos daily. These photos are going to be available for you for download and for you to use. And new this year, we have editing going every day, so they're actually being posted throughout the day as events take place. You can get to them from our homepage. It says conference photos, so you can just click there and use those, please. It's also linked from the media resources page. Our media office, which is next door, some of you have already visited, is open today until 5 p.m. We'll be open tomorrow following the keynote from 10 to 5, and then on Wednesday and Thursday from 9 to 5. We also heard from many of you last year, and there will be continuous beverage service and snacks all week in the next door. Immediately following this press briefing, please join us next door for box lunches, and we can continue networking. And if there's additional questions that anybody has, please feel free to bring the conversation next door. And with that, I would like to introduce Michela Taufer, our SC19 General Chair and Jack Dongera Professor in High Performance Computing at the University of Tennessee.
Thank you, Amanda, and good morning and welcome to Denver and welcome to SC19. I want to thank you all for coming at SC19 and for joining us today here. And I want to extend a special welcome and thank you to our media partners, Admin HPC, AI Trends, Bio IT World, Enterprise AI, HPC Wire, Inside HPC, Linux Pro Magazine, Mind Commerce, Scientific Computing World, and the Next Platform. So this year, SC19 come together thanks to the help of 784 volunteers, including 175 student volunteers. Quite an exciting team. We have 374 exhibitors, 1,150 presenters, and 12,750 attendees as of yesterday evening. So as the conference moves forward, we expect this number to grow. Our theme this year is HPCs now, and these are 3 little magic words that represent a major impact for the lives of everybody. At this year's conference, we will not only learn about the latest discovery of our evolving fields, but also celebrate the countless ways in which HPC is improving our lives, our community, and our world. I hope you had the time and opportunity to, over the past year, to read our blog. If you haven't, it's never too late. And so I encourage you to go and look at our blogs. Throughout the interviews posted in our blog, we learn from some of the top researchers across the globe how HPC is playing a critical role in cancer research, the development of connected and autonomous vehicles, predicting the occurrence and impact of natural disaster, understanding how the universe was formed, exploring high-performance molecular dynamics simulation and visualization, and optimizing the impact of AI and machine learning technology. And I can assure you this week, this was only the tip of the iceberg, and there is much more at SC19. While navigating SC19, our attendee can this year keep the conference on the palm of their palm or their hands with our new mobile app. So download the mobile app and use it to connect with the attendees, with exhibitors, plan your week, and navigate this amazing conference. I hope you will join us with this evening at 5:30 in the Mile High ballroom for our HPC is now planning. And the title is When Technology Kills. This will be quite an engaging, exciting discussion with a panel of experts. We will have a special reserved area in front today evening for you and other special guests. We will keep your seat until 5:15. So if you arrive before 5:15, please join me in front in the Mile High Ballroom. Don't miss the keynotes tomorrow morning. It is in Mile High Ballroom as well. It starts at 8:30. And we will hear from Dr. Stephen Squire, the principal scientist for the Mars Exploration Rover project. His talk is about how HPC has moved to the edge to enable exploration of Mars. Again, you are invited tomorrow morning to join me in front. Seat will be reserved until 8:15. New this year are we offer exciting guided media tour on the exhibit hall, and it is on Tuesday and Wednesday at 11 a.m. and 2 p.m. To join the tour, please plan to be here 15 minutes here, meant at the room here next door, 113, 15 minutes before the start of the tour. Again, it is at 11 a.m. and 2 p.m. The room where we gather is 113, 15 minutes before. So I hope you will be able to join us for our tours. If you can't make a tour, I just want you to consider to visit the student cluster competition. This year, the student cluster competition is repeating a paper of SC18, and it is connected to our keynote, as they are modeling Mars, starting from images, satellite images collected by NASA. So it's an exciting opportunity to see the work of the students, and at the same time, connect also with the talk of Dr. Squire. Other things that I encourage you to see is SciNet, the SC Theater, and of course our Startup Cafe on the exhibit floor. I would like to thank the top 500 for joining us today. And now it is my pleasure to introduce our first speaker, Sergio Boixo, who is Chief Scientist, Quantum Computing Theory at Google AI Quantum, to discuss the recent Google Quantum Supremacy experiments. Sergio.
All right, thank you. Good afternoon. Thank you very much for the invitation and the opportunity to talk here. I'm going to talk about this recent paper we published, Quantum Supremacy, using a programmable superconducting processor. So the basic idea, this is a benchmarking experiment. So it's related, it's in the infancy, I will guess, of quantum computing, but it's related to the top 500 benchmarking. That we're going to hear about. So in a nutshell, what we're doing is, after 30 years that physicists have been promising on the power of quantum computers, right? I'm approaching billions of dollars of investment. For the first time, we're seeing the first signs of the computational power of quantum computers. After 30 years, physicists can say, promises made, promises kept. So that's part of the idea of this experiment. This is, of course, a large experiment that involves a lot of work from a lot of people. So here is the team at Google, a lot of folks on the hardware team that actually built the chip, the quantum computer, based on superconducting qubits and the control system, and they actually made the experiment work, but also people are working on theory and simulations. So this is a benchmarking experiment. We're benchmarking a quantum computer. So let me try to give you a little bit the philosophy of this benchmarking experiment. I guess I'll start with a crash course on quantum computing in 30 seconds. So in quantum computers, instead of bits, which can have binary values, 1 and 0, we have qubits. And you can think of a qubit as a vector in a sphere, right? So those are the little balls we have on the left. When we execute a quantum circuit, which is the quantum version of a classical circuit, we first initialize all the qubits, let's say to the state 0, so all the vectors pointing up. And then we execute quantum gates on our qubits. So this is a quantum circuit diagram, and the boxes represent quantum gates. They're similar to classical gates, but they're the quantum version. They're matrices acting on these vectors. The white boxes are single qubit gates, so quantum versions of a knot, for instance. They change the state of one qubit. And the lines, like the blue boxes, connecting 2 qubits, so going from left to right, that's the time direction of a qubit. The lines connecting the 2 qubits, those are 2 qubit gates that will create entanglement and allow us to do general quantum algorithms. So you execute a quantum circuit, and then you measure. When you measure, you kind of collapse the wave functions. You collapse the computational state of your quantum computer, and you're going to get bits. You get 1 bit of information for every qubit. So you're going to get a bit stream of zeros and ones. In our case, we're going to be doing benchmarking with 53 qubits, so measurements up to 53 qubits. So measurements, every time we measure, we will get 53 bits. And we can repeat the measurements because quantum mechanics is probabilistic, and so are quantum circuits. When you repeat the measurement, you may get a different bit stream. But the quantum circuit specifies which bit streams are more likely. That's how you perform your computation, by designing a circuit that makes more likely the correct answer. So this is the crash course in quantum computer, and that's what you normally do. You just run a quantum circuit, and normally you run a carefully chosen quantum circuit because you might want to solve a specific problem. So for this particular experiment in quantum supremacy, for this benchmarking experiment, we're going to do something a little bit different. Instead of running a carefully chosen quantum circuit, we're going to run a randomly chosen quantum circuit. So what we do is the single qubit gates, which now have question marks, we're going to choose them at random for some predefined set of single qubit gates. So they're chosen at random, but we know what quantum circuit we run, and that's very important. We choose them at random and we write the quantum circuit. And as before, our random quantum circuit will specify some bit streams with higher probability than others. And that's the computational task. In the quantum computer, you can run this quantum circuit, you will get bit streams. Are you getting the probable bit streams? Are you executing the correct quantum circuit? And you can execute the same computation in a classical computer with simulations, and the computational task is the same, to produce bit streams which are high probability bit streams according to this quantum circuit. So why we choose random quantum circuits? Well, one reason is because this is a well-studied problem in complexity theory. We have guarantees for complexity theory that this is a very complex problem, an exponential time problem on classical computers. So it's hard for classical computers, but at the same time, it's kind of the hello world program for quantum computers. It's kind of the simplest thing you can do in a quantum computer. If you don't know anything about quantum computation, at least you can try to program, random circuits. So that's the benchmarking experiment, and this is sort of the flow of the experiment. The task is to sample the output distribution of a quantum circuit. We're going to run this task on an experimental quantum processor. That's Sycamore, the processor that was used for this experiment. And we sample bit streams, we collect bit streams, and we record them, and we know what circuit was chosen. And we compare with classical computers. So we will use the best available simulation algorithms. We will run them on classical hardware, including Summit, also Google data centers and collaborations with Jülich supercomputing centers and others. And then we evaluate the result of this benchmarking. And if the quantum processing time is short, and it's going to be around 200 seconds to sample 1 million bit streams on a quantum computer, but the corresponding classical processing time is unfeasible in practice with current supercomputers and the best algorithms available, then we declare quantum supremacy. This is a name coined by John Preskill in 2012. All right, so this is Sycamore, the chip that we're going to use. It has 54 qubits, 53 qubits were used in this experiment. It has 196 control knobs. We're controlling not only the qubits, but also the connections between the qubits, the couplers, which is what allow us to do these 2 qubit gates. So if you have been following the news, last year we announced a chip called Bristlecone with more qubits. Actually it had 74. This chip has less qubits, but it has more control knobs because we're controlling the couplers. We have cables controlling the couplers, whereas in Sycamore we are controlling the qubits, but not the couplers. And it turns out that when you run algorithms on all the qubits at the same time, controlling the couplers was one of the key new technological improvements that allow us to be able to perform this quantum supremacy experiment. So one lesson is that more qubits doesn't equal more computational power. Control and errors is really critical. Okay, so this is how we perform the task on Sycamore. The great cruxes that you have there, those are our qubits. They are superconducting circuits. The boxes in different colors, those are the couplers that now in Sycamore have control knobs. They actually have a cable that allows us to control the coupler between the qubits. We initialize all the qubits, so all the crosses in the state 0. We apply single anti-qubit gates on the qubits, so as before, the time is going from left to right as we apply gates to our qubits. We apply single qubit gates with microwave signals, like the weekly signal on the left, that takes around 25 nanoseconds. We also apply 2 qubit gates with the control knob that we have on the couplers. Those are the signals that you see far on the left and the bottom. It takes 12 nanoseconds, very fast 2 qubit gates. Then we measure, and we're going to get a sequence of 0 samples, 1 bit per qubit. We repeat this around 1 million times. That will take 200 seconds to do in Sycamore with the current control. It could be faster, that's the number we get today. And then we do a classical simulation of the same circuit on a large classical computer or a supercomputer. And this comparison actually allows us to measure what is the probability that there was no error on the quantum circuit. So this is a benchmarking experiment in 2 ways. We're benchmarking the computational cost by measuring the computational cost of an equivalent classical algorithms, but we're also measuring what is the probability of not having an error. This is called fidelity in quantum computing. So it's a benchmarking the quantum computer itself, and that's very important. So it's kind of a system test. We're measuring the probability that as we put all the components together, there is no error anywhere. And we call that the fidelity. We measure it with something called the cross-entropy score. It's a measure related to machine learning. So this is how we perform the experiment. First, we're going to verify the quantum computer. So that's the horizontal line. What we're going to do is we're going to simulate classically tractable circuits. We run them in the computer, and we can simulate them because they're classically tractable. So we keep the depth, the number of cycles, the depth of the circuit fixed at 14 cycles of single anti-qubit gates, and we increase the number of qubits. And we verify that the quantum computer is working. We do this system test, and we measure the probability of not having an error. Once we're happy that everything is working correctly, and we reach 53 qubits with everything working, so the system test is successful, then we're going to increase the depth of the circuit. We're going to add more gates at 53 qubits. For the currently available algorithms, increasing the depth makes the simulation much, much harder. So we push into the supremacy regime where we cannot feasibly simulate this sampling task anymore with classical supercomputers. So this is the verification path. We start at 12 qubits. We go all the way to 53 qubits at fixed depth of 14 cycles. Now, in current experimental quantum processors, every gate has some probability of error. The y-axis is the fidelity of the probability of an error. As we add more gates, the probability of not having an error decreases because every new gate has some probability of error. So that's what we expect. We expect, in the best case, a decay of the fidelity, an exponential decay of the probability that we don't have an error. So we simulate the quantum circuits. We take data, 1 million bit streams or more, with the classical computer. Sorry, in the experiment with the quantum computer, and then we simulate the same task with the classical computer, and we calculate the fidelity. The red circles are the fidelity for a full quantum circuit. And so that's experimental data, 8 by classical simulations. We also simplify the circuits. One thing we do, for instance, is we break them in half. So instead of one circuit of 50 qubits, we'll have 2 of 25 by removing something like 20 gates. So the probability of error shouldn't change too much because we remove only 0.2% of the gates, or 0.3 or something like that. But the simulation becomes a lot easier because now you have 2 independent circuits with less qubits. So that's one example of a simple circuit, and we see that indeed these simple circuits, although they have much lower complexity and much lower entanglement, they have the same fidelity as the full circuits, which are more complex, exponentially more complex, and they have a lot more entanglement. So that's an interesting finding of this experiment, which we expect, but you really have to test it in the experiment. And then we have the black line, and that's very important. So the black line is the optimistic prediction, let's say. This is called the digital error model. And what we do is we measure the probability of error of all the individual gates. And in the best case, when you put them together, you don't introduce new errors. And if that's true, you just have to multiply the errors of your components if you're doing everything correctly, which is very hard. And that's the black line, that's the prediction. And we see that the prediction, the digital error model, matches really well, up to 10–20%, the simulations with the full circuit. So one conclusion is that complexity does not introduce new errors, quantum mechanics still works, and quantum computation is possible. So once we have done the verification step and we are satisfied, then we push in that in the supremacy regime. Oh, I should mention, sorry. The largest simulations we do there for 53 qubits, that's 40, that's 5 hours running on 1 million cores. So sort of the equivalent of, I don't know, around 100,000 desktops. So that particular simulation was quite expensive. And that's per circuit within 10 circuits, so 50 million core hours. Okay. Now we push in the supremacy regime, so we increase the depth. As I said, for the algorithms that we have available, the complexity increases. We cannot simulate the full circuits anymore, but we run them and we save the data. It's actually now publicly available, so if other people are capable of doing these simulations, they can check our predictions from the experiment. But we can simulate the simpler circuits, like when we cut them in half, and we do that. And we also see that it matches the discrete error model, so the analytical model where you multiply the probabilities of your components. So we believe that the experiment is working exactly, although we cannot test it anymore because the quantum circuits in this case are too complex for the available algorithms. But we publish the data and we encourage the community to test the experiment. So what are the implications of this experiment? Why are we excited about it and why we work so hard for so long on this experiment? So implications for computer science are the following. From a fundamental point of view in computer science, if you want, an abacus is equivalent at a fundamental level to a modern computer. Of course, a modern computer is an amazing piece of technology and is doing billions of operations per second, right? But the basic operations are equivalent. It's an equivalent computational model in terms of efficiency. And what physicists promise in the 80s is that quantum computers are not like that. Quantum computers is a different computational model. So in a sense, a quantum computer is farther from a modern computer, at least for some problems, or for some specialized problems, is farther from a modern computer than a modern computer from an abacus. And that's what we see in the experiment, because a small chip, which is an experimental quantum computer, can perform at least some specialized computations unfeasible for classical computers. And technically, this is called, we challenge choose to thesis. We don't disprove it, we will need error correction to disprove it, but we challenge the choose to thesis. There are implications in fundamental physics in the following sense. Since the beginning of quantum mechanics, early last century, there is this question of, okay, so electrons, atoms behave quantum mechanically, but everyday big objects, they behave classically. So there is some frontier between the quantum and the classical, and where is this frontier? That's an important question, right? So one possibility is that this frontier is in complexity. While you make more complex quantum systems, maybe they become classical. Maybe an electron has like a spin, it's 1 degree of freedom. That's quantum mechanical. But when you increase the complexity, there is a transition to the classical world. And that's possible, and will means that, quantum mechanics works at a smaller scale. Quantum computation is not possible, right? So you have to test it. And we do that in this experiment, and we push this frontier in complexity by a factor of 10 billion. And this is very important. We believe that is true, but you have to test it in the experiment. Every time you push a theory to a new regime, you have to test it because there may be surprises. Nature might not agree with your theory. So we do it, and it changes. And then there is a very important implication for us at Google from a practical point of view, which is an engineering implication. This is a system test. We check that all the components work and we can put them together correctly. So in a sense, it's similar to the first flight of the Wright brothers. This is not a useful computation, this is still an experimental quantum computers, but we saw that a new model of computation is possible. And of course, there is a lot of work to do to make it practical and commercial successfully. But it's a first flight. The technology is possible. It's a system test. So what's next? Well, in this graph, you sort of see the complexity of quantum computation and where we're going. The x-axis is the number of qubits. We're at 50-something. And the y-axis is the probability of error. And if you get your errors per gate, right? If you get your errors low enough and you do the system test and everything is working, you enter a regime where you cannot simulate some problems classically anymore. So that's what is called the quantum supremacy frontier. We're going to keep scaling the number of qubits and reducing the errors. Both things are important. Looking for near-term applications, what is called NISQ applications. And the final goal is to build a fault-tolerant quantum computer, which will require around 100,000, a million physical qubits. So we have a long ways to go. And errors of around 0.1%. But that's the point where we have algorithms in paper that work well. So how we're going to get there? Well, it's going to be hard, and it will require a lot of effort from academia, government, and industry in collaboration. And there are many unsolved problems, but they are not unsolvable problems. That's sort of what we saw in this experiment. It's hard, but not impossible. Why would you bother to go along this route? Well, I will just mention one area of applications, which is Feynman's killer app. That's what Feynman proposed in 80-something. If you can simulate quantum mechanics, you can improve computational chemistry, material research, pharmaceuticals. Actually, these are simulations that are done in the top 500 supercomputers all the time. So we think that that can give birth to a new industrial revolution, an energy-efficient revolution where we're not blind anymore in the way we design chemical processes, let's say by trial and error, but we can actually simulate them at the quantum mechanical level. So thank you very much.
Session, and thank you, Sergi. And I would like now to turn it over to the top 500, Green 500 HPL projects, and the leaders of these three projects, Eric Strohmeyer, Jack Dongara, Horst Simon, Wu Feng, Martin Moyer, and Michael Leroux. If you want to join us, please. And I let you present the result of your list. We will investigate in this session.
Well, good afternoon. I'm not going to show the slides. Traditionally, we do that our both session tomorrow, so that's the advertisement. I'm going to give you the highlight, and of course you all know because the list has been published and the press release has been out since this morning. But the big news is there is no big news. At least that's what it looks like at the beginning. The top 500 keeps changing. We had an average turnover compared to the last couple of lists. We lost 101 systems because they are too small. But that doesn't mean that everything keeps changing as it used to, because the big news was, or the big gap was, that there is no news at the top. Not in the top 10, but if you go down the list, you have to go to position 24 to find the first new system. So the first 23 systems have been on the list 6 months ago, and some of them much longer. There are actually two changes in those first 23 positions, because we lost two very old, but still very powerful systems, the K-computer system, as well as the Titan system in British National Labs. So two systems got decommissioned out of the last 25, and no new ones up to number 24. If you look at the other categories in the list, things are settling in a new normal, which is Chinese manufacturers are very important. China also installs a lot of systems, so China is a very important market, but it hasn't dramatically changed since the last couple of lists. If you drill down in the list, and we're going to do that tomorrow in more detail, you can actually look at the commercial systems, the commercial market, compared to the research systems, the military market, and you see that those two markets actually are very different. The commercial market is dominated by China as a marketplace, as a consumer, and by Chinese companies producing those systems, while the numerical market, the scientific market, is still dominated by US-based manufacturers and by the US and the international community as a marketplace, not by China. So we see actually a very different behavior of the commercial market and the numerical market, the scientific market, in the last couple of years, and we're going to look in more detail in those aspects. One of the aspects we are doing nowadays, which changes much more frequently than the top 500 itself, is, for instance, the Green 500, because within the Green 500 we really look at technology. So you want to talk about that, or should I? I can summarize and you can correct me. Yeah. So if you look at the Green 500, which is up to, if you want to do it.
Okay. But the Green 500 has quite a bit of change in the top. There's 4 new systems that occupy the top spots. Off the top of my head, I don't have the exact numbers, but I think what's particularly notable is there's a system that many of you reported technology about, the ARM-based technology, the Fujitsu A64 FX processor. That has come to fruition, and you see that in the number 1 slide. And interestingly, of the top 10 computers that are in the Green 500, it's the only one that is not accelerator-based. All the other ones are accelerator-based. That sounds not odd? Or just, I'm just not being loud. So that's an interesting development that for the first time in a while we have a non-accelerator-based system that's occupying the first spot. We've seen this massive increase in accelerator-based systems over the years, but this is an interesting development from the perspective that this is ARM-based technology that is driving supercomputers. A little further down the list, the 3rd and 4th positions are 2 new supercomputers from academic institutions. So Rensselaer Polytechnic Institute and MIT. There's a consortium based MIT/University of Massachusetts, I believe, a number of different Massachusetts universities that have partnered together to develop a supercomputing center in the Northeast with which to push forth high-performance computing for the region. Off the top of my head, there's a thing about it. You may have other things that you could add, or
No, I think that's the highlights. So the Green 500, the top 10, the first 4 positions are actually 2 new systems. That's the big news there. It doesn't necessarily mean that the average power energy efficiency has increased that much, but it's interesting to see which technologies come in and achieve these rates.
Yeah, one of the excellent points. One of the things I will note is that as a green person, it's over the last 4 or 5 lists, it's been, I don't know if I want to call it disappointing, but it's just that there's been a leveling off, or flattening off of efficiency. And just in talking to folks in the community, it seems as though power, for whatever reason, is not as much of a first-class citizen, arguably, as it started to be. We're talking about exascale computers, supercomputers right now, not at 20 megawatts, not at 30 megawatts, but now at 40 megawatts. So that means that to get to 40 more megawatts, we're looking at 25 gigaflops per watt as a performance bar. We're currently at about 17 gigaflops per watt, so it's relatively close. But far short of the 20 megawatt figure, which would have been 50 gigaflops per watt instead of 25 gigaflops. And I think some of the trends are also such that we don't see as frequent as reporting of the power on the high-end systems, which is something that would hopefully be able to reinvigorate. We have had a number of systems, however, that have gone to great lengths to measure their power of their supercomputers at much finer granularity than ever before, and it has implications with respect to procurement of systems for people's data centers.
And the details are going to be discussed in the Green 500 POF on Wednesday evening, right?
Wednesday at 5:15 to 6:45.
So another set of data and the statistics we started collecting is the HPCG benchmark, high performance conjugate gradient benchmark, and Mike Carew is one of the fathers of the benchmark. So
hello, thank you. So not a lot of change to the top machines. The top 3 are the same, and we lost the K computer. Same reason. There's a new machine at CEA that is number 10 on that list. The biggest change I think we've seen is stuff that's still behind the scenes that I think we'll start to see results of, and that is vendor participation from ARM, from AMD, from Intel as they roll out their new accelerator capabilities. All of these teams have active development in creating optimized versions of HPCG. All of those vendors will have representatives at the BOF on Thursday afternoon at 12:15, so you'll be able to hear some of the techniques they've been using. What it's also led us to see is that there are some optimization strategies that are emerging because of discrete memory systems that I think we'd like to put into openly available reference implementations so that more people can have access to them. We anticipate, with Fugaku in particular, I'm expecting an incredible number. Maybe I'll be disappointed when that machine comes online. Overall, the list has grown. There are, I think, 160 entries, so still not, we'd like to see more. We'd like to see many more of the smaller machines. So if you have any influence over the smaller markets and to get them to run this benchmark, before they ship a machine out the door, I think that would do the community a lot of service to see some of the performance profiles at the smaller system size. So come Thursday if you can.
thank you, Mike.
I might add just really briefly, across all the top 500 and the Green 500 and HPCG, one of the things I think we're really seeing is this potpourri of different offerings on from the CPU side to the GPU side to the accelerator side, and I think that's what makes HPC right now a really exciting place to be. And so while I may have been a little bit of a damper on the fact that the energy efficiency of systems seems to have plateaued at the top end, I think that this proliferation and potpourri of different accelerator-based and CPU-based platforms is really helping to innovate this space, and it would be an exciting next 5 to 10 years, I think.
Okay, and I think with that, we're going to switch to Q&A. And
well, maybe I could just make one small
sure.
comment. We have a new benchmark, which is trying to look at some issues that impact machine learning. And the benchmark is focused on trying to use short precision and see how far we can push short precision. So some of the hardware that we have today is looking at not 64-bit, not 32-bit, but 16-bit floating point arithmetic. And machine learning focuses on using 16-bit arithmetic. So we have a lot of vendors pushing 16-bit floating point arithmetic. So we put together a benchmark that exercises 16-bit floating point arithmetic and tries to use one of the components used in machine learning during the training session, that is matrix multiply, and trying to focus on how far we can push 16-bit, not only for machine learning, but for scientific computing in general. So can we, in fact, leverage 16-bit arithmetic in scientific computing, getting reasonable performance, that is enhancing the performance because of the advantages of 16-bit arithmetic, and still maintain accuracy? So there are some mathematical techniques that can be used to enhance the precision that we get, enhance the accuracy that we get from the 16-bit to try to drive it up to what you would have gotten had you done the computation in 64-bit. So it's a new benchmark called HPL minus AI. If you went to bit.ly/HPL minus AI, you would see the benchmark. And there's some rules there, and it follows HPL to a large extent, but it does exercise things in 16-bit arithmetic. So the idea here is to push that and see how far we can benefit from hardware that's really in place for machine learning and to use that for scientific computing.
so do you have a BOF about that?
No, there's no BOF about that yet. So we have one entry in the list, so it's the top one at this point. So we did a stunt using Summit, trying to do a large computation with the benchmark to understand what the performance is. So the Summit, of course, is the #1 machine. It gets around 140 petaflops on the LinPack benchmark. Is that right? Yeah. And this benchmark that I just talked about gets the same accuracy that you would have gotten had you done it in 64-bit arithmetic, but it's 3 times faster. So you get the benefit of enhancing, you get the speed benefit because of the 16-bit and then doing this mathematical technique to the accuracy. So the top is.
Thank you, Jay. Person?
Since I'm here, if I want to make 2 comments actually. One is just to reflect back, and this is the last supercomputing show of the 10s and 20s. So if we go back and look to the year 2010 or 2009, we'll see around where these were the beginnings of the exascale and exaflop initiative. And I think the decade ends with some disappointment, because if you go back 10 years ago, everybody was hoping and planning to get an exaflop system by now. We don't have an exaflop system by now. And some of you know that I bet against the exaflop system. I'm winning my bet. I just haven't cashed in yet. So we don't have an exaflop LinPack system. So now we can have a long discussion and analyze why we didn't get there. But I'd like to be more optimistic and look forward to the next decade. And I think that's my second comment. The 2010s were the decade of the accelerators. And most of the performance gains and also the gains that we made in terms of energy efficiency in the Green 500s were the basis of accelerators. So this was an architectural innovation that is about 10 years ago. So if you remember, I think it was 2009, we had the first accelerator petaflop machine with a Roadrunner in Los Alamos. And so now we're a decade later, the accelerators have fully matured. They are very well represented in the list, and they are deriving from some of the top systems today. So what's coming next is what Jack was already alluding to, is we're getting into the 20s, and the 20s will be the decade of AI architectures. And so the architectural innovation is in the space of artificial intelligence and adapting our computer architecture to efficient execution of AI machine learning programs, I should say. Jack explained correctly that this is where there's a lot of excitement. So I would expect us as a community to adapt to this new technology and go through things of actually simulating 64-bit on 16-bit machines efficiently, and still gain the performance gains and the efficiency gains that we're hoping for. So let's not forget accelerators, but let me say, why is machine learning so important? It's very simple. As the HPC community, we all benefited from the big investment in accelerators, which was driven, if we're going to just reflecting on the decade, which was driven first by graphics, then by games, then by Bitcoin mining. So things that have nothing to do with what we're doing here, but they formed a commercial basis that the HPC community could leverage into a good architecture. And I think we will see the next thing, the next decade, there will be a huge demand for machine learning type architectures, and the HPC community can leverage that investment into more powerful and more energy efficient processing in the next decade. So, my perspective.
Thank you, Horst. I think with that, we're going to switch to question and answers, and Sergio's going to be.
And I would like to invite Sergi, and we can now open the floor to questions. See a question there?
Hi, Tiffany Trader with HPC Wire. So, Wu, if with the mini Fugaku, if I may call that, on the top of the green 500 list, do you have a sense of how ARM plus GPU would do in terms of energy efficiency?
Oh, that's a good question. That's a really good question. That's not something that I had actively thought about, but as Horst had pointed out, I mean, this past decade has been the decade of accelerators, and so comparing the two, you would expect to see substantial improvements in the efficiency. That may be sufficient enough to get us down to the 30 megawatts.
So optimistic, and I'm seeing a couple head nods. All right.
Yeah. That's an interesting thing because the efficiency that's been gained by mini Fugaku, that was done without the accelerators, and yet we've had a lot of the gains with the accelerators and efficiencies this decade. So you combine the two, that's certainly very evocative thought in terms of driving efficiency in HPC.
Thanks. Other questions?
Can you comment on the impact of the memory subsystem of the non-GPU accelerated system on the power efficiency? Are we seeing better utilization for us? Is that on the entry?
Yeah, so I would say that the answer is, I'm going to say at a high level, yes. But I think a lot of that will also depend on what the workloads are and how, when we get these irregular graph-oriented workloads, you have this, or AI workloads, you have this tendency to stress the memory subsystem more, and you'll have the benefits of the energy efficiency there that will be more pronounced when running on that kind of platform versus a traditional memory subsystem platform. So, data movement, especially on chip, is of course very expensive. So, point is well taken. So depends on a lot on the benchmark. That's part of the reason why we're talking about HPCG, we're talking about the AI benchmarks, and HPL.
And I see there another question.
Yeah, really crazy, something consulting. You mentioned 16-bit precision. The Intel DL Boost is using 8-bit precision floating point. Is there any intention to benchmark that solution? And you mentioned some functionality that you could derive additional accuracy out of 16-bit. If you care to comment on some of that.
Yeah, so I don't have any real information on 8-bit floating point, but we haven't tested it. We haven't really pushed that level. It gets a little dicey, as you can imagine. So So there are two standards, I'll call them, for 16-bit arithmetic. One is the IEEE standard, and the other thing is something that Google has in its TPU called bfloat 16. And that has different ways of representing that 16-bit representation for floating point. I'm not going to comment on the details, but there are two separate things. And one has more accuracy than the other. One gives you more dynamic range than the other. So those are sort of trade-offs that you have to make, and that has an impact on the accuracy. There's some mathematical techniques that you can use to get a solution and then go through an iterative process to refine the solution. The refinement is done at a higher precision. So the thing you'd like to do is to do the bulk of the work in the lower precision, and then use the higher precision for just some of the work, and then refining the solution. So you can do that. And again, there's mathematical techniques. It's called iterative refinement, and it's a well-known technique. It's been around for a long time, but now maybe is a good time to use it. So that's one thing that we're pushing to understand how you can do that. It just mathematically, it's attempting to get the correction to the solution. So you're computing a correction, not the solution. And that correction, it's a small number, so the short precision may be able to resolve it better. Is in a nutshell.
Any other question? We have still a couple of minutes, so please.
So very interesting to hear Sergio's presentation. Several recent future architecture designs assume that the quantum is going to be one of the accelerators. In your presentation, you clearly stated that classical is not equivalent to quantum. So if we have a classical fusion supercomputer with a number of accelerators and quantum is one, what is going to happen to this non-equivalence?
Well, there's a lot of work to be done in this part of the question, but that's indeed the way we envision to work as an accelerator and advancement. In problems like in chemistry, there are already many hybrid or hierarchical methods. So that have been developed over the years, where you do maybe some semi-classical solution at the level, and then you specialize until you have a quantum core of highly correlated systems. So the idea would be to still use similar methods that have already been developed. And then once you get to the quantum part or the problem, then you outsource that to the accelerator. Another example would be, for instance, you want to do protein folding, then you're probably not going to do protein folding in a quantum computer because it's a large time scale problem with dynamics. But you might be able to use a quantum computing accelerator to improve the flow speeds. And then you do the bulk of the computation, molecular dynamics, on a classical computer or supercomputer, but leverage quantum computers accelerators to improve flow speeds. That's the way. So I think that's probably the direction, at least in this area, to move.
Is there someone else? I already have a question.
Please.
Sergio, so it's a two-part question. First off, the choice of the 200 seconds for the runtime, was that arbitrarily chosen, or was that done on the basis of threshold, say, as a noise factor for thermal effects specifically, where we're kind of accumulating, adding noise in the system? So how was that number less than 200 seconds chosen?
It's just the experimental number that we have today, which is going to improve.
But it wasn't based on any impact of the noise?
No, this is, well, our computations, because there is noise, indeed they have to be fairly short. Every computation itself is much shorter than the 200 seconds. It's of the order of microseconds.
But you're iterating.
But we iterate and sample around 1 million of the strings, so we do it 1 million times.
Yes.
And we're building the control system, and it's a complicated setup to really control superconducting qubits. So there are several inefficiencies that we haven't had time to address. It could be faster because every measurement is just order of microseconds. So 200 seconds is just the time it takes today to measure 1 million data streams with a control system we have.
Sure, so the 200 seconds is arbitrary.
Yeah, it's for 1 million data streams.
Okay. And the second part is, I'm wildly happy Feynman's point of conjecture is true. From conversations with like Matthias Meyer and other people, where commercially viable for dealing with fertilizers and other chemical systems, atom systems of interest, it's around 768 robust qubits. Do you agree with that as kind of a bar for commercial utilization? And second part of my question is, given the current state of your 54 qubits, when do you think you might get to that bar that you set for us?
Right, so there's a long path and there are many moving targets. So we have, of course, to distinguish, I think you call them robust qubits or logical qubits. So qubits without errors, those are logical qubits. Roughly today, with the techniques we have today for error correction, the equivalence is around 1,000 physical qubits per logical qubit.
So you're not there yet, right?
So we're clearly not there yet. That's the long roadmap we have to a fault-tolerant computer, which will require around 100,000 or 1 million physical qubits, which will be equivalent to 100 or 1,000 logical qubits.
And that's kind of the bar that you're seeing for commercial viability.
We hope to find commercial viability earlier. So those are the things we know today. But we keep lowering the bars on both sides. The hardware is improving, the technology is improving, the errors are lower, we are learning a lot about how to scale systems. At the same time, the quantum algorithms are improving, and they have been improving by orders of magnitude over the last 5 years, by at least 4 orders of magnitude. So, I think with the algorithms that we know today, probably with around 100 logical qubits, we are going to start see applications with the algorithms that we can see in paper that they work. But something very interesting is happening as we are improving experimental quantum computers, noisy NISQ, noisy intermediate scale quantum computers. Now we can also try algorithms, and we can try heuristics, which we are not able to explore in paper anymore. And we're fairly optimistic about that. But maybe in 2-3 years, we will see hopefully NISQ applications which you cannot prove with pen and paper anymore, but you try them and it works. And something similar happened, I think, with the first classical computers. People tried Monte Carlo, was one of the things they tried. And they tried it because they had a computer where it made sense to try Monte Carlo. So that's the direction which we're going. We do have actually already a first practical application, which is a bit niche, but nevertheless important, which is a follow-up of the supremacy experiment. Initially we thought it's just a benchmarking, but actually Scott Aronson came back and said, well, actually, if you can do this, then you can do certifiable random numbers, which is something that you can only do with quantum techniques. You can certify that they are quantum and therefore random. And randomness is actually quite important for computing security. So I don't think it's going to be the final solution for all the effort in quantum computing, but we're very happy that it's the first true practical application, and we can get it working in hopefully in a year or so.
I say thank you for your answers to the complex problem, and I should identify it as something that you love for a decade.
We have one comment.
Yes, I have a question to my congratulations on this breakthrough to you and your team. So you very clearly said that what you find is like a rule on computer.
Right.
So let me ask a very simple question that you can answer here. This is, when do you expect quantum supremacy for calculation that would say pass what was here at this conference to go to Belfast? That's a real something. On a small molecule or a fraction of molecule that traditional supercomputer would be able to do. How far away are we from that?
So there are, two ways to try to do that. One is in the digital model, which is what I've been talking about, which you decompose your program in gates that is overhead. I would say, if you're optimistic, then hopefully let's say 3 years. That's the next complication. There's a lot of work to be done and a lot of problems that need to be solved, both on the algorithmic side and on the experimental side. But I am optimistic, so hopefully in 3 years. There's also analog simulations that you can do today. In superconducting qubits, analog platforms, supercomputing qubits are more controllable. There are other interesting platforms that are less controllable, but maybe have less intrinsic noise. And I think, in the analog realm, I think we're even closer. And actually, people are already using analog simulations to check classical algorithms. So they are not beyond what you can do with a classical algorithm, but maybe there are questions, is this a valid approximation for this problem? And we're already at the point where maybe you don't know the answer because you're making too many uncontrolled approximations, but then you can perform an experiment and compare. And that is already happening in analog simulations.
So in 3 years, we'll be done.
3 years.
So why don't we conclude with the optimism of Sergio, this conference press. I invite you to join us the next door for continuing this discussion and having a lunch with us. Thank you so much to our presenter and thank you for participating in this press conference. Have a great day.